physics concept that we decided to investigate is the conservation of momentum. We conducted this experiment by hitting a golf ball at two watermelons, 133.5 inches from the center of the second melon. By applying the notion of impulse and conservation of momentum, we wanted to find the average force that the golf ball hits the melon. Experimental errors emerged as a result of shooting the video in 1000 frames per second slow motion. After recording the video, we could not find sufficient technology and software that could handle the full 1000 frames per second, and so we had to settle for software that can only read 100 frames. Therefore, our numerical values for the velocity and time of contact are close estimates based on utilizing the ratio between 100 frames per second and 1000 frames per second. Now here's the trial.
The law of conservation of momentum states that for a collision between two objects, the total momentum before the collision equals the total momentum after the collision. In addition, by looking at Newton's third law, which states that the force between two objects is equal and opposite, we can say that the golf ball and melon have equal but opposite momentum changes. Since the force of the golf ball on the melon is equal and opposite to the force of the melon on the ball, then the time of impact has to be the same as well. Therefore, each object experiences an equal but opposite change of momentum, or otherwise known as impulse. Using the equations momentum equals mass times velocity and impulse equals average force of impact times time of collision, we can find the average force that the golf ball hits the melon. We can solve for impulse by saying that impulse equals change in momentum. Therefore, by multiplying the mass of the golf ball by the velocity of the golf ball, the impulse can be found. Therefore, using this concept of change in momentum, we set this impulse, which came out to be 3.029 kilograms meters per second, to the impulse equation, which is force of impact times time of contact between the melon and the golf ball. Since the time of contact was 0.005 seconds, the impulse of the golf ball was divided by the time of contact in order to get the force of impact the golf ball inflicts on the melon. The force of impact of the golf ball on the melon ended up being 605.7 newtons of force.
This next trial was particularly intriguing because it appears as if there is a force field around the melons and momentum is transferred from the first melon to the second melon. It is interesting to see that momentum is not lost but in fact conserved and transferred over to the second melon. Our hypothesis is that the golf ball hits the stake below the first melon over a longer time of contact, causing a smaller force to act on the first melon, resulting in no damage. While the ball bounces off to the side, the force is then transferred to the second melon over a smaller time, causing a large force to ultimately produce the crack seen here.